All right, guys, here it is. I'm going to go to page 528 and read number 19. Look, I made tons of lines for us to write stuff. I'm going to go down here from the get-go, and I'm going to draw a normal curve, put a 0 in it, 1, 2, 3, 1, 2, 3. I want everybody to just draw a normal curve right there. We're definitely going to use that to figure out which way to shade, figure out how to do the normal CDF. Okay? Here we go. Our one problem we're going to do together is number 19. The Cranky Mower. A company has developed an easy start mower that cranks the engine with the push of a button. Love that on the snowblower. The company claims that the probability this model of mower will start on any push of the button is 0.9, so apparently it works 90% of the time with one push. A consumer testing agency suspects that this claim is exaggerated, but they're lying basically. To test this claim, an agency researcher takes a random sample of 20 of these mowers and attempts to start each one by pushing the button. Only 15 out of that 20 start. Now look how this says part A, part B, part C, part D. This is the whole thing, guys. State hypotheses, define the parameter, show that the normal condition basically is not met. When large counts condition is violated, you shouldn't perform a one sample z-test about a proportion, but you can carry out a significance test using the binomial distribution. Okay, that's silly. What we're going to do is we're going to write that it's not met, and then we're just going to go anyway, but put a disclaimer in there, like we do with the random condition. Now, assuming the null hypothesis for part A is true, calculate the probability based on your result. So I'm not following these directions. I'm going to do an entire write-up for this, with the null hypothesis being it works 90% of the time, and the alternate hypothesis being, no, I think it's less than that. I think you exaggerated. All right? Looking at your outline, the first thing you do is name the the population, and then the parameter, and talk about what kind of test you're going to do with hypotheses. So let's name a population here. Go look at the sample. They took a random sample of 20 of these mowers. Okay, our population is all, not just the 20 that got picked, all easy start mowers. That's all I got to do. I just got to take the sample and think about where the sample came from and write that as my population. The next thing I'm supposed to do according to this list, I'll bring the list back in for each one of these maybe even, name the parameter. It's always a mean or a proportion. Well, they said that this happens 90% of the time and we think it's less than 90. And then it went 15 out of 20. Those are percentages. So this isn't a mean problem. It's not an average problem. It's a proportion problem. The parameter we will draw conclusions about is the proportion of mowers that start with one push. Or on the first push of the button, or however you want to name it, but the context should be in there. The parameter is proportions, but proportions of what? Proportions of the mowers that actually start with one push. Okay, so back to my list. I named the population, I named the parameter. I'm going to say that I'm going to perform a significance test at the level 0.05, and I'm going to name my hypotheses. I'm going to do all that in one sentence. Ready? We will perform, let's name it, a one proportion z-test at the level 0.05 on the following hypotheses. Like you fit those on this line right here. The ho is that this works 90% of the time versus the ha, well, I can't fit it on that line. The proportion is less than 90% of the time. Always have the null hypothesis be a parameter variable, mu or capital P, never x bar, never p hat. Always have the null hypothesis be an equal sign. We went over this a couple of days ago. So then the alternate is the one that's less than or not equal to or greater than. Okay, so according to my list, I named my population all the mowers. I named my parameter the proportion of the time that they start with one push. I'm going to perform a 1 proportion z-test at the level 0.05 where the ho is 0.9 and the ha is less than 0.9. And I gave that the significance level in this spot. Here's what I got to do. Verify the random condition, verify the normal condition by doing some multiplying, and then go find a test statistic and a p-value. So here we go. Let me see what they said about the random condition. To test the claim, an agency researcher, so somebody who knows what they're doing, took a random sample of 20 of them. We're going to trust an agency researcher taking a random sample. So the random condition is verified by the random sample. So I'm done with the random condition. Okay, for the normal condition. All right, here we go. For the normal condition. What am I supposed to multiply together? N times P naught. Okay, the N is 20, and the P naught is 90. 20 times 0.90. Okay, 20 times 0.90 is 18. That's bigger than 10. And N times Q naught would be 20 times, well, if that's 90%, this is 10%, so 0.10. And 20 times 0.10 is 2. Okay, we cannot verify the normal condition. Because that's a 2, right? That's over 10, but that's not. So we oops, I said can. So let me just make that can't real quick. Sorry about that. We can't verify the normal condition. So here's what we say about that. So our results may not be accurate. I'm going to finish it anyway. I mean, if somebody gave me this data and said, hey, I want you to do this statistics, and that's what they're paying me for, yeah, I'm just going to finish out this thing, but I'm going to put in there, yeah, my results might not be very good, just so you know, because you didn't take a big enough sample. All right? I mean, what kind of lazy guy can't take a bigger sample? You're just pushing buttons on a machine, for God's sake. Anyway, so let's see where I am on my outline. I named the population, all of the easy mowers. I named the parameter, the proportion of them that start with one push. I said I'm going to do a 1 proportion z-test at the level 0.05 where the ho is 0.90 and the ha is p is less than 0.90. I verified the random condition. We got a little issue. These are not both bigger than 10, so I can't verify it's a normal curve. If it's not a normal curve, I really shouldn't be using a normal CDF. See what I mean? That's how important that is. I'm going to use a normal CDF anyway, but if the shape is off and it's skewed and I used a normal curve, my results may not be accurate, right? So now I got to find a test statistic and a z statistic and a p-value. Our z statistic is, well, I'm going to write z equals here, and then I'm going to go down here and do that work because it's not going to fit on that line. So z is equal to p hat minus p naught over the square root of p naught q naught over n. The p hat we got, what is this problem, was 15 out of 20, so we should write that somewhere. I'm going to go up here, I'm going to go p hat was equal to 15 out of 20, and on my calculator I'll figure out what 15 divided by 20 is. It's 0.75. They said it works 90% of the time, and we did this random sample and only works 75% of the time. So I set up this whole thing, but before I just yell that, hey, that's less than 90%, I think you're lying, I actually go and use the theory and find the probability that you would find something that low to add math numbers to our case before we call these people liars. So this goes 0.75 minus the null hypothesis proportion is the 90% that was suggested, so it's minus 0.90. It goes over the square root of that 0.90 goes here, and then the Q naught would have to be 0.10, so they add up to 100%, and it's over the 20 snowblowers that, lawnmowers that they actually try. Okay, I can put all this in the calculator in one entry, and it goes like this. Open my parentheses. 0.75 minus 0.90, close my parentheses. Divided by the square root of 0.90 times 0.10 divided by 20. It's that easy, guys. You can put the whole thing in the calculator in one entry. Take a look at it. The numerator in parentheses, the division sign, and the square root, and this follows the order of operations. The calculator knows to go this times this divided by this in that order. And I get negative 2.24 is what I'm going to call that. All right, so I got negative 2.24. Now, let me go to my normal curve. There's negative 1, there's negative 2. Negative 2.24 would be somewhere around here, so I'll put z equals negative 2.24. And then I'm going to shade toward the tail. I want you guys to do that every time. So our z statistic, always show your work somewhere. You guys won't have these lines and everything, so you just be writing this in the middle of a page. I would actually put this in the middle of my paragraph if it wasn't for these lines. Okay? Our p-value is. Now I do not need to multiply by 2 because my alternate hypothesis is strictly less than. It's not the not equal to sign. Our p-value is the probability that z would be less than negative 2.24. It's the shaded part is a probability, and so I'll even draw it right here. Look, that's the p-value. It's the probability that I would get a z less than negative 2.24. And so how do I find that? It goes normal CDF. Because we're going this way, I put in negative 100 first, and then negative 2.24, and then a 0 to 1. So I'm going to go to my calculator and find out what that is. Second, and variables, normal CDF, negative 100, negative 2.24, 0, and 1. And the calculator tells me it's 0.0125. Okay, so going back to our outline. I named the population, I named the parameter, I named what kind of test I was doing. I got a 0.05 for this. I got hypotheses. I verified the random condition, the normal condition. The test statistic was negative 2 point something. The p-value is 0.0125. Now, I have to reject or fail to reject the null hypothesis. Well, that's less than 0.05. So I write it this way. With p equals 0.0125 being less than alpha equals 0.05, we reject the null hypothesis that p is equal to 0.90 and conclude that the alternate hypothesis is true, that it's less than 0.90, that the proportion of mowers that start on the first try is less than p equals 0.90. So we can call him a liar. We did an experiment, we got data, we ran a complete significance test. Now, so we have enough information to call them liars. Now, you guys have named populations and parameters. You did that in section 8.1. You named hypotheses, and you interpreted p-values. You did that in section 8.2. In section 8.3, you learned how to talk about the conditions and the z statistic, which is right here, and the p-value, which is right here. And so now, your job today is to put it all together in one written statement. All right? The last page of your notes today, I'm not going to do. Here's one for you guys to just do on your own. If you go back to page 525, I'll show it to you. At the bottom of the page, there's a who feels job stress. And now this is going to be another proportion problem. Look, you can already see it, 75%. A random sample of 100 employees, 68 answer yes, so p hat is going to be 68 out of 100. We have an alpha, a significance level that's not 0.05, it's 0.10. And then this says the proportion of all employees in this chain is that differs. So it doesn't say it's greater than 0.75, it doesn't say it's less than, it wonders if it differs. So your alternate hypothesis will be not equal to. So I'm going to give you a couple of hints to start this. In the first place, don't forget to write your normal curve at the bottom and use this drawing to make sure you do your normal CDF stuff right. The z statistic is p hat minus p naught over the square root of p naught q naught over n. You guys can do that one all right. The alpha is 0.10. The p hat for this problem, when you read it, is 68 out of 100. And so that's 0.68. And I'm just going to tell you, your null hypothesis will be that p equals 0.75, because they tell you that in the problem, and that your alternate hypothesis is that p is not equal to 0.75 because they ask if it differs. If they're asking if it differs, they're asking if it's different. So it could be bigger or it could be less than. That means when you get your p-value, you multiply by 2. All right, you have all of the notes, you have the outline, you got a big old blank piece of paper here. So that's your homework. Your only homework for today is to do that write-up. All right, we'll talk tomorrow. Have a good day.